Okay, we are moving on to one of the last sections in our exponential unit, and we're going to be connecting all of these exponent powers and connecting it with graphing and being able to analyze a graph and analyze equations to see if they represent an exponential function. Your learning target today, you can identify. That means if I give you an equation, you're going to tell me, does that equation represent an exponential function? You're also going to be able to evaluate. Evaluate, remember, just means plug in. So I'm going to be giving you an exponential function, and you're going to evaluate it for some given value. And then you are also going to be able to graph exponential functions. So you got a lot that you're doing today. You are identifying. That's more of a level 1, 2, just telling me, does it look like the equation is supposed to look? Level evaluating is like a level 2.5, 3, and then graphing is definitely that level 3 stuff. I would say evaluating is pretty much level 3 too. So an exponential function, this is great introduction to 9th grade. You get to do this lesson all over again when you get to 9th grade. This whole unit, actually, you're going to be doing all over again. You start with this chapter 7, so you're going to start with exponents, scientific notation, and then you're going to end it with this stuff. But notice the 8th grade standards is called linear algebra. That's the course that you're in. That means our lines that we deal with are linear. They're just perfectly straight. When you get into 9th grade, if you remember registering, it was called exponential algebra. Exponential means that you're not dealing with just straight lines anymore. You're dealing with exponential lines, meaning, look how exponential lines are. They go up really fast or they decrease really fast. Okay, so in 8th grade linear algebra, we have that constant slope, y equals mx plus b. And when we bump it up to exponential, it means that you don't have a slope. You go up really fast or you go down really fast. Okay. So an exponential function is a function of the form y equals a times b to the x, where a is bigger than 0. That means this has to be bigger than 0, and b is also bigger than 0. B can't equal 1, so I can't have a 1 here. And x is a real number. Okay? A real number means that it's rational. It's going to be some kind of rational number. Here's an example of exponential functions. So this is a positive exponential function. Notice this. I have 2 to the x. That means that it just keeps growing and growing and growing. Because you keep multiplying by 2, it's really a geometric sequence. You remember that you change terms by multiplying or dividing. So clearly 3 times 2 is smaller than 4 times 2, and it's just going to keep getting bigger and bigger because I keep doubling it. Or, notice if it's a negative 1, it's just flipped. It's the same graph, it's just flipped on the x-axis. Here I have y equals 1/2 x. That's smaller than 1. So 1/2 x, anytime that it's smaller than 1, it's going to be a decreasing value. So 1/2 means smaller than 1. I start big and then I keep halving it. So it keeps getting smaller and smaller, but it will never touch the y-axis or the x-axis. It will never become 0. It'll get super duper duper close to 0, but it will never become 0. And then again, the flipped case. So the flipped case would be that negative. Part of your first learning target, being able to identify exponential functions, is if you're given a graph, can you say, hey, this would be your exponential function, or this, no way, that's a linear function. That's what I just did in units, 6, 5, all those stuff. Exponential goes up really fast or down really fast. It starts slow, and then all of a sudden it goes fast, okay? All right, so part of identifying exponential functions from a table or an equation. You want to see if the x value increases at the same rate. The rule for the x value is see if you add or subtract the same number all the time. Write that down. You see if you add or subtract the same number all the time. And then the y value is that difference, and that connects us to that geometric sequence that we've identified before. The y value is a common product. So you make sure x is being added or subtracted by the same thing, y is being multiplied. Then it's exponential. Or it has to match that equation. So two things that you're checking for. If it's a table, you're checking that x increases by adding or subtracting by the same number, and y is a common product. If you're given an equation, you check to see that your equation looks exactly like this, except it's going to be numbers in there. So notice, where is x on this equation? Where's x? As the exponent. X is the exponent, exponential function. So x always has to be the exponent for an exponential function. Okay? All right, let's analyze this first one, this first table. So when I look at this first table, x should be increasing by the same thing, added or subtracted. So I plus 1, plus 1, plus 1. It meets the x criteria. Y has to be being multiplied. So what did I multiply -1 by to get to -3?
3.
3. So times 3. -3 times 3 is -9. -9 times 3 is -20. This represents an exponential function. The next one, y equals 3 times 6 to the x. So until you memorize this, which you will, you can just look at the general form. It should look like this. Do I have something times something with x as the exponent? Yep, I sure do. So this is an exponential function. Okay? So then the next one is an equation. So I'm checking that equation to make sure that it matches that template. Y equals a times b to the x. So I have y equals a number, then I have x down here. I don't want x down there. X has to be an exponent. So this is not an exponential function. An exponential function has to have x as an exponent. So this is no, no, no. Okay, the next one. So this is a table, so I try to see if it meets that criteria. X should be being added or subtracted by the same number. Plus 1, yes, all the way down. Now I check to make sure that y satisfies that it has to be multiplied by the same number. 1 times 1 is 1. 1 time, but then it's times 3. It doesn't work. No, this is not an exponential function. Because notice that it has to be a common product in order to be an exponential function. That's learning target number 1. I'm going to give you tables and an equation, and you're going to tell me if the table or equation is an exponential function. Learning objective number 2, evaluating. That just means plug in. So you're going to really need to know how to use your calculator's power button. I'm going to pause here for a second, and you're going to get a calculator if you need one. Okay, so suppose 30 flower beetles are left undisturbed in a warehouse bed. The beetle population doubles each week. The function f of x equals 30 times 2 to the x gives the population after x weeks. How many beetles will be there after 56 days? So this is an exponential function because it looks like a times b to the x. So a is my 30, b is my 2. And now I have to evaluate for 56 days, but this is weeks. How many weeks are in 56 days?
56.
8.
Oh, weeks.
Yeah, because you go 56 days divided by 7 days in a week is 8 weeks. So I'm really evaluating this exponential function for 8. So I'm going to plug this 8 into the equation. So it's going to be 30 times 2 to the 8th. So you really want to know how to punch this into your calculator. What I would do, remember order of operations says to do powers first, exponents first. So what I'm going to do is 2 to the 8th first in my calculator, 2 to the 8th, and then I'm going to times it by 30. Actually, you can plug it in. The calculator's program. 30 times 2 to the 8th is 7,680 beetles. I told you, exponential, it grows fast. Exponential growth. It goes, whoosh, it scoots up really fast. Okay, the next problem that we're going to use to meet that evaluating standard. An initial population of 20 rabbits triples every half year. The function f of x, look at me, f of x equals 20 times 3 to the x, gives the population after x half years. So I like to maybe highlight half year is what this is related to. How many rabbits will there be after 3 years? So how many half years are in 3 years? 6, right? Because there's 2 half years of 1. So 3 times 2 is 6 half years. So that's what I'm going to plug into this exponential function. So I'm going to plug my 6 in. So it's going to be 20 times 3 to the 6. 20 times 3 to the 6 is 14,580 rabbits. Do you feel like you can punch this into your calculator okay? And evaluate? That's plugging in. Okay, that's learning objective number 2. So we've done 2 learning targets. We've done identifying and we've done evaluating. Now we get to graph. We get to do the last one.
Yay!
So graphing connects it with evaluating. They're pretty much one and the same, except you have to plot it. The graphs are not going to be perfect. It's an estimate. Just heads up. So if you're one that really wants your point to be in the exact spot, good luck. It's not going to happen. It's going to be, we're all going to get an approximate right graph. So what is the graph of y equals 3 times 2 to the x? So we need some values. What I would suggest doing, -2 to +2. Okay? So I want x is xy. -2, -1, 0, 1, 2. And you're just plugging it in with your calculator. Write this down. So, the first one, 3 times 2 to the -2. I'm going to type that in. 3 times 2 to the -2 is 0.75. The next one, 3 times 2 to the -1. 3 times 2 to the -1 is 1.5.
I see that.
3 times 2 to the 0 is 3. Because I know 2 to the 0 is nothing, so it would just be 3. 3 times 2 to the first is 6. 3 times 2 squared is 12. And then you plot these and connect them. So -2 and 0.75 would be something like that. -1 and 1.5 would be about right there. 0, 3. 1, 6. Notice, see, it's growing really fast. It's getting so much faster. 2 and 12 is going to be up here. So your graph is going to look like this. Yeah, it's just going so fast.
Like a race car. And room.
Okay, and the last one that we'll do here, computer mapping software allows you to zoom in on an area to view it in more detail. The function